Convolutional neural networks, or CNNs, have revolutionized the way we process and analyze visual data. From facial recognition to self-driving cars, CNNs are at the heart of many modern AI applications. But what makes them so powerful? The answer lies in their ability to learn complex patterns from large datasets. However, even the most advanced CNNs can struggle if the training data is limited or lacks diversity. This is where data augmentation comes into play, offering a solution to enhance model performance and reliability. Data augmentation refers to a set of techniques used to artificially expand the size and diversity of a training dataset. By applying transformations such as rotation, flipping, scaling, and color adjustments, we can generate new, varied samples from existing data. This process helps CNNs generalize better, reducing the risk of overfitting and improving their ability to handle real-world variations. Essentially, data augmentation acts as a powerful tool to make models more robust and adaptable. Imagine training a CNN on a limited set of images. The model might perform well on those specific samples but fail when exposed to new unseen data. This is known as overfitting, where the model memorizes the training data instead of learning general features. Data augmentation helps address this issue by introducing variability, ensuring that the model learns to recognize patterns rather than specific examples. This leads to improved accuracy and reliability in practical applications. There are several popular data augmentation techniques used in CNN training. These include geometric transformations like rotation, translation, and flipping, as well as color adjustments such as brightness and contrast changes. Each technique introduces unique variations, helping the model become more resilient to changes in input data. By combining multiple augmentation methods, we can create a rich and diverse training set that better represents real-world scenarios. Rotating and flipping images are simple yet effective ways to augment data. By rotating images at various angles or flipping them horizontally and vertically, we can simulate different perspectives and orientations. This helps the CNN learn to recognize objects regardless of their position, making the model more flexible and accurate in real-world tasks where objects may appear in unexpected ways. Scaling and cropping are essential augmentation techniques that change the size and focus of images. By resizing images or cropping different regions, we expose the CNN to various object sizes and positions. This encourages the model to learn features that are invariant to scale and location, which is crucial for tasks like object detection and classification in dynamic environments. Adjusting the color and brightness of images introduces further diversity into the training data. By varying these attributes, we can simulate different lighting conditions and camera settings. This helps the CNN become more robust to changes in illumination, ensuring consistent performance across a wide range of real-world scenarios, from bright sunlight to dim indoor lighting. Adding random noise to images is another effective augmentation strategy. Noise injection helps the model learn to ignore irrelevant variations and focus on the essential features of the data. This technique is particularly useful for improving the model's resilience to real-world imperfections, such as sensor noise or compression artifacts, which are common in practical applications. Random erasing involves masking out random regions of an image during training. This forces the CNN to rely on multiple cues rather than focusing on a single part of the image. As a result, the model becomes more robust and less likely to be fooled by occlusions or missing information, which can occur in real-world scenarios. Advanced augmentation techniques like mix-up and cut-mix combine multiple images to create new training samples. Mix-up blends two images and their labels, while cut-mix replaces a region of one image with a patch from another. These methods encourage the CNN to learn more generalized features and improve its ability to handle ambiguous or blended inputs. Real-world projects, data augmentation is often implemented using specialized libraries and frameworks. Popular tools like TensorFlow, PyTorch, and Keras offer built-in functions to apply a wide range of augmentation techniques. By integrating these tools into the training pipeline, developers can easily enhance their datasets and improve model performance without manual intervention. Numerous studies have shown that data augmentation can significantly boost the accuracy of CNNs. By exposing the model to a wider variety of samples, augmentation helps reduce errors and improve generalization. This is especially important in fields like medical imaging and autonomous driving, where high accuracy is critical for safety and reliability. Overfitting is a common challenge in deep learning, where the model performs well on training data but poorly on new data. Data augmentation combats overfitting by introducing randomness and variability, forcing the model to learn more general features. This leads to better performance on unseen data and greater confidence in the model's predictions. In many real-world datasets, some classes are underrepresented, leading to imbalanced data. Data augmentation can help balance the dataset by generating more samples for minority classes. This ensures that the CNN receives sufficient examples from all categories, improving its ability to recognize rare or less frequent patterns. In working with small datasets, data augmentation becomes even more crucial. Limited data can restrict the learning capacity of CNNs, leading to poor generalization. By artificially increasing the dataset size through augmentation, we can provide the model with more varied examples, enabling it to learn richer and more robust features. Transfer learning involves using pre-trained CNNs on new tasks. Data augmentation plays a key role here by adapting the model to the specific characteristics of the new dataset. By applying relevant augmentations, we can fine-tune the model more effectively, ensuring it performs well on the target task. Medical imaging often suffers from limited and imbalanced datasets. Data augmentation is widely used to overcome these challenges, generating diverse samples that help CNNs detect subtle patterns in medical images. This leads to more accurate diagnoses and better patient outcomes, highlighting the real-world impact of effective augmentation strategies. Autonomous vehicles rely on CNNs to interpret complex visual environments. Data augmentation helps these models handle diverse driving conditions such as different weather, lighting, and road scenarios. By simulating various situations, augmentation ensures that the model can make safe and reliable decisions on the road. Retail and e-commerce, CNNs are used for tasks like product recognition and recommendation. Data augmentation helps models adapt to different product images, backgrounds, and lighting conditions. This leads to more accurate search results and personalized recommendations, enhancing the overall shopping experience for customers. Security systems use CNNs for tasks like facial recognition and surveillance. Data augmentation helps these models recognize faces and objects under different conditions, such as varying angles, lighting, and occlusions. This improves the accuracy and reliability of security applications, making them more effective in real-world environments. CNNs are increasingly used in agriculture for tasks like crop monitoring and disease detection. Data augmentation helps models handle variations in plant appearance, lighting, and background, ensuring accurate analysis across different environments. This supports more efficient and sustainable farming practices. Manufacturing, CNNs are used for quality control and defect detection. Data augmentation helps these models recognize defects under different conditions, such as varying lighting, angles, and backgrounds. This leads to more reliable inspections and higher product quality, reducing waste and improving efficiency. Sports analytics relies on CNNs to analyze player movements and game footage. Data augmentation helps models adapt to different camera angles, lighting, and player positions. This enables more accurate tracking and analysis, supporting better coaching decisions and performance evaluations. Wildlife monitoring uses CNNs to identify animals in images and videos. Data augmentation helps models handle variations in animal appearance, backgrounds, and lighting. This improves the accuracy of species identification and supports conservation efforts by providing reliable data on wildlife populations. Fashion industry uses CNNs for tasks like clothing recognition and trend analysis. Data augmentation helps models adapt to different styles, colors, and backgrounds, ensuring accurate recognition across diverse fashion items. This leads to better recommendations and trend predictions, supporting designers and retailers. CNNs are used in art and culture for tasks like artwork classification and restoration. Data augmentation helps models handle variations in style, color, and texture, ensuring accurate analysis and restoration of artworks. This supports cultural preservation and enhances our understanding of artistic trends. Educational applications use CNNs for tasks like handwriting recognition and automated grading. Data augmentation helps models adapt to different writing styles and formats, improving the accuracy and fairness of educational tools. This supports personalized learning and efficient assessment. Social media platforms use CNNs for content moderation and recommendation. Data augmentation helps models handle diverse user-generated content, including different image styles, filters, and formats. This leads to more effective moderation and personalized content delivery, enhancing user experience. Entertainment industries use CNNs for video analysis and content creation. Data augmentation helps models adapt to different video styles, lighting, and effects, ensuring accurate analysis and creative outputs. This supports innovative content production and enhances audience engagement. Financial institutions use CNNs for document analysis and fraud detection. Data augmentation helps models handle variations in document formats and quality, improving the accuracy of automated analysis. This leads to more reliable fraud detection and efficient document processing. Logistics companies use CNNs for package tracking and inventory management. Data augmentation helps models adapt to different package appearances and environments, ensuring accurate tracking and efficient management. This supports smoother logistics operations and better customer service. Communication platforms use CNNs for tasks like image-based messaging and content filtering. Data augmentation helps models handle diverse image types and formats, ensuring accurate filtering and effective communication. This leads to safer and more efficient digital interactions. Cloud computing platforms use CNNs for image analysis and storage optimization. Data augmentation helps models adapt to different image sources and qualities, improving analysis and resource allocation. This supports scalable and efficient cloud services for a wide range of applications. Smart devices use CNNs for features like facial recognition and gesture control. Data augmentation helps models handle different user appearances and environments, ensuring reliable performance across devices. This leads to more intuitive and secure smart device experiences. Robotics applications use CNNs for navigation and object recognition. Data augmentation helps models adapt to different environments and object appearances, ensuring accurate perception and decision-making. This supports safer and more efficient robotic operations in various settings. Environmental monitoring uses CNNs to analyze images of natural scenes and detect changes. Data augmentation helps models handle variations in weather, lighting, and landscape, ensuring accurate monitoring and timely detection of environmental changes. This supports conservation and disaster response efforts. Real estate platforms use CNNs for property image analysis and recommendation. Data augmentation helps models adapt to different property styles, lighting, and image qualities, ensuring accurate analysis and better recommendations for buyers and sellers. Marketing teams use CNNs for campaign analysis and audience targeting. Data augmentation helps models handle diverse marketing materials and formats, improving the accuracy of campaign analysis and personalized targeting. This leads to more effective marketing strategies and higher engagement. Teamwork and collaboration platforms use CNNs for document analysis and content sharing. Data augmentation helps models adapt to different document types and user-generated content, ensuring accurate analysis and efficient collaboration among team members. Health and wellness applications use CNNs for tasks like activity recognition and health monitoring. Data augmentation helps models handle variations in user activity and environment, ensuring accurate tracking and personalized recommendations for users. Tech platforms use CNNs for content analysis and adaptive learning. Data augmentation helps models handle diverse educational materials and formats, improving the accuracy of content analysis and supporting adaptive learning experiences for students. Customer support platforms use CNNs for image-based issue resolution and automated responses. Data augmentation helps models handle diverse customer images and scenarios, ensuring accurate issue identification and efficient support for users. Researchers use CNNs for scientific image analysis and discovery. Data augmentation helps models adapt to different research images and formats, improving the accuracy of scientific analysis and supporting new discoveries across various fields. Innovation-driven companies use CNNs for product development and testing. Data augmentation helps models handle diverse product images and scenarios, ensuring accurate analysis and supporting innovative product design and testing processes. Summary: data augmentation is a vital component of CNN training, enabling models to learn from diverse and realistic data. As AI continues to evolve, new augmentation techniques and tools will emerge, further enhancing the capabilities of CNNs. By embracing data augmentation, we can build more robust, accurate, and reliable models that drive innovation across countless industries.